right, shall we get started?
Yes.
All right, welcome. It's our first RAG Meetup in San Francisco, so we're really excited about it. We're going to talk about what we do at Zeta Alpha, but it's a bit more general about the whole space of RAG and how you can make those systems really work, go beyond the proverbial 5 lines of codes and make it really production ready in terms of quality, especially. We're not going to talk so much about the LLM ops stuff, but a little bit at the end. My name is Jakub Zavrel. I'm the founder of the company. I've been in the AI space since the early 90s, so I'm afraid to admit. And actually worked on neural networks for search in 1995. So I'm kind of stubborn, I guess, to still keep working on it. And before this, I had a company called TextKernel, which pioneered the use of AI in the recruitment space, matching people and jobs. Eventually sold that to Career Builder. And well, what do you do as an AI entrepreneur? You start another company. So that's Zeta Alpha. And here with Fernando, our CTO, who's been with us from the very beginning. And for those of you who don't know the company, we are based in Amsterdam. We have a flexible relationship with San Francisco since late last year. And basically our core mission is to connect people and knowledge in very knowledge-intensive companies. Things like chemistry, pharma, high-tech engineering, but also legal. These are domains where the internal expertise and knowledge is super important. And these companies are now looking to basically turn that internal expertise into generative AI capabilities to help people get stuff done, to automate their external processes, and just kind of have an institutional memory of what they're doing inside companies. So we started out as a kind of academic search engine for AI research papers. We still do that. So if you want to try out our platform through our website, you will land in a kind of a public index that indexes all the archive and machine learning conferences. So you might find that interesting. By now, we work more and more for companies like BASF and Deloitte, and really large knowledge-intensive companies. Basically, our platform is a knowledge discovery and organization platform. So these 2 pillars. So it's not just a search engine. It's actually a collaborative tool for teams, especially R&D or engineering teams, to not only discover and stay up to date around information, but also to organize into concepts like tagging stuff, keeping notes, reading documents, and sharing with your colleagues and all these kind of things. And you have, of course, search and recommendations at the heart of it. And this sort of new style of large language model-based search engines really offers a lot of productivity benefits, because instead of going through the search results, you just get the summarized answers with the references to your internal documents. And there's a lot more different components like visualization, analytics, people search that kind of play into this knowledge discovery ecosystem. And
so are you taking questions? Or?
Yeah, sure.
So when you mean existing internal documents, can I search a corpus outside of my company, get it in and say, this is my list of external documents that what kind of, I don't know the right word for it, ratified or said, these are the possible external documents you can also
you can crawl external data.
So do you help in getting that?
It's also federated search, so you can connect multiple search indexes, internal and external. So for example, you can combine search on your internal data with web search or search in a proprietary, like industry-specific database. And of course, that internal data, if you talk about companies like life sciences or high-tech engineering, that's very confidential data. So this whole thing is like deployable on-prem with full sort of enterprise IT security, single sign-on, and all these kind of things. And that allows to not only do all these things which we thought of, but also to basically power the GPT experience of internal data. And that's been kind of in the last year or so the main argument to want to do this for companies. You can kind of ask questions of various types to your whole information ecosystem, but you can also talk to individual documents, get summaries, do that across languages, AI regulation of People's Republic of China. You can quickly get translation. And it doesn't stop just with text. You can obviously, with large language models are no longer just language models, they're large multimodal models. And you can just as well converse with the information in figures and tables and graphs, and you can ask questions about it. You can extract information out of it with handwriting. Because it's not just a search engine, it's also an organization engine. All of these things that are extracted or annotated, they're also stored as additional information on the documents and then reusable as knowledge and memory for yourself and the rest of the organization.
Do you do handwriting recognition or no? If you scribble notes on the thing?
Yeah, so I mean, if you basically select a piece of the page that has handwriting, you send it to a multimodal model, they're pretty good at that. And you can kind of extend this conversational search metaphor to build collections around projects to discover which information is relevant, how to search, and keep up to date. Basically, it's like a long-term organization system where you also get updates if something new comes up, which is relevant to the work that you're doing. So basically, this is a very rough schema of the platform. So it's kind of a enterprise search architecture with a cluster of different services which load your documents from many different applications through connectors or web crawlers or whatever you have, and respects the access rights on those documents so that once you get into your search engine, unlike let's say the vector search engine that's common, you have all those metadata from your file store, from your access rights, from your other structured information. You can take it into account when you're searching. But of course, to provide the semantic search, it's also important that you produce embeddings using good neural models for that. And then the platform exposes this all this functionality through APIs that allow you to search, filter, do hybrid search, re-ranking, chat, and build custom bot types that do very specific business-specific logic, retrieving and synthesizing information.
Right.
Yeah.
Under what situation do you need a candidate search?
I'll come to that in a bit. Yeah. So, more or less, the start of the show is RAG, Retrieval-Augmented Generation, because of course we can ask any question to a large language model, but if it's not being trained on the proprietary data of the company or the data that is up to date, it cannot answer those questions. But through by sending that same question to a search engine, we can retrieve the relevant internal proprietary documents and then template them into the prompt and then produce the answer, right? This is pretty common. I think you guys are all familiar with RAG. And of course, this has led to this renaissance of search relevance engineering, because when you're doing RAG, and this is kind of the typical prompt template where you give some instructions on how to construct the answer from the search results, which are then templated here at the bottom. And you have irrelevant search results in the template. Let's say that when we're looking at this one, the green ones are the good guys and the red ones are irrelevant. Well, if you template the answer also from irrelevant documents, you're going to get wrong answers. All right, so basically the sort of naive RAG approach is vulnerable to bad search results. It will produce hallucinations. Yeah.
And if you could kindly go to one back on your slide, you turned green and red and you did neural search. Is that where you're combining the output of LLM and neural search to make that decision, or is it just
No. This is, let's say, human judgment for now. Like I find those documents relevant or not. So you can, of course, do all kinds of prompt engineering to make the RAG system less vulnerable to this. This is a technique kind of derived from chain of thought, right? If you let the large language models say something like think step by step or take a deep breath or some of those things, then you ask it to basically provide some intermediate reasoning steps, and then it can create higher quality results. That's a kind of solution for this, because you can say, well, just skip the irrelevant documents, right? But then you're actually, it leads to much better results, but because the generation of tokens is linear, the time is linear in the amount of tokens, it also leads to a lot higher latency. So you get like search results after 60 seconds or something when you do this properly. So that's not really the way to go. What if we can get more green ones and less red ones, right? That's very attractive. And that's why we need neural search, because typically when we have natural language questions, like here, what's the best way to reduce my AWS cost? You don't want to get a document which has very high lexical overlap that shares a lot of keywords. Like what is the best way to reduce travel costs? Almost all the words are the same, but you want to get a document like our monthly cloud expenses in Amazon, Azure, and GCP, which has zero lexical overlap. And that's why we need semantic search, right? And neural search is basically a relatively easy way to get some form of semantic search, right? So are you guys all familiar with embeddings in neural search? So basically the query and the documents are mapped to this high-dimensional space using embedding models. And then we do similarity search of distance, cosine similarity in that space, for example. And this allows us to go across keywords. You get kind of synonyms and related terms for free. You can handle very complex questions because the point in the space will encode not only the words, but also their relationship. And you can even do it across languages or across modalities, right? Your query can be text and your document can be an image or a piece of audio. As long as you have the right representation in this space, it works.
So just so that I understand the passages you did, do you do the query answer thing and then you compare the question against the query and provide the answer snippet? Is that the way you're doing it, or?
Yeah.
Yes. Okay, so you run it before, right? I mean,
Yeah, the documents are of course processed at indexing time offline, right? There's a lot of the millions of documents. You process all of them. Then you have an index where this lookup can go very fast.
no, but what I meant is that document you send through a question answer scheme where every paragraph has a relevant question which it answers. And then you see the relevance of the questions and then provide those passages only. So it's a prior step that you have to do with the LLM. Like you have to send.
Yeah, I mean, if you're talking about chunking and embedding the chunks, and then you do a search and only pick the chunks that are relevant, I think that's what they do, right?
Yes.
You don't take a whole document.
Well,
and
nobody can tell you a priori which documents are relevant,
No,
right? You just get.
Say something different.
No,
What I'm saying is that you take the chunks and you run it through an LLM before, and you say, what are the type of questions this chunk will answer?
Okay, yeah, but that's something very different.
Okay,
I'm
okay, that's
gonna
what I wanted
get
to
to that, but you're reading my mind.
Okay, okay.
But this is not about how you do the
Okay,
search.
okay, I see.
The basic search is very simple.
Simple.
You embed the documents, you embed the query, you compare the distance in the space, okay? All right, so there's indexing techniques, HNSW. There's this whole class of vector databases. If you have people who are starting with RAG, the first question they ask is, what vector database should I use? And how do I do the chunking? That's a good question, but it's not the most important question because all of the databases, search engines use HNSW more or less. And there's an approximate way to do that kind of similarity search very fast. And I think even Oracle these days has vector search. And,
so I'm gonna push back a little bit, right? Chunking is extremely important. If you don't chunk right, you have a proliferation of embeddings, your tensors. And if you don't chunk right, you blow your context window.
So the context window used to be 4,000 tokens a couple months ago. Now it's 100,000 tokens. So I agree it's important, but there's not like the most important thing is that your results are relevant. Now how you do that, that's a lot of details of these.
Yeah, so if I chunk paragraphs, this is a whole page, right?
Yeah.
But now I'm feeding the LLM. And if the only thing that's important in that entire page are 2 sentences, I'm feeding the LLM a lot of unnecessary information.
Yeah.
And there's cost of that. This is why I'm saying is when we are implementers, right? We are a service company. And the challenges we find is chunking is probably one of the most important things. If you don't get that right, you have downstream problems.
But there's many more details, like if you have PDF, and you convert it with the wrong PDF converter to text, you also have problems, right? So there's many details of how you can lose quality. I'm gonna fast forward to this. So the classical keyword search is typically a 2-stage process, right? Where you have a keyword index and a re-ranker that's typically machine learning based. The reason enterprise search was not very good in the last decades because this is very easy, but this you need a lot of data. And in companies, typically you don't have a lot of supervised data to train those kind of good re-rankers. So now with neural search, basically the structure is still the same, except that this first stage is being exchanged for a vector database. And this second stage is typically done using also a large neural model, which looks at the query and the document, and it's called the cross-encoder. This guy is called the encoder. And these vector databases, there's a whole proliferation of new databases, like Weaviate and Quadrant, others. But by now, everybody has caught up. So there's this kind of vector search in every classical search engine like Elastic or OpenSearch. We actually use OpenSearch as the core. And a lot of these more classical databases and search engines have the advantage that they also are very mature in terms of how you can do data schemas, how you can do filtering, how you can, manage the indexes and scale them and all of that. And especially when you talk about enterprise search, and security is very important. Security is about filtering, right? So you're not allowed to give information to somebody just because it's close to the query, but you also need to always filter by access rights, and these guys have better cars for that.
Could you elaborate on that cross-encoder model?
Yeah, I will do that in a second. So basically, the bi-encoder takes something like usually a BERT style model in practice, and processes the query and the documents independently. The documents are processed in indexing time, produces a vector stored in the vector database. At query time, you use the same network usually to process the query, and then you compute the consign similarity. The cross-encoder is different because it also uses the BERT style or different network, but it basically this a little bit. It basically processes the query and the document at the same time. So it just concatenates them with a special token in between. And the output of the network is not a vector, but it's actually a score, a single score, how relevant that document is to the query. And it's trained on some search data. This is, of course, much more powerful because you can, in the transformer network, calculate all the relationships between the query and the document. Here, you cannot do that. So these guys are a lot better, but they're also a lot slower because you need to do it for every query document there in your top ranked documents.
So have you found like one or two models performing better than the others, cross-encoding?
So cross-encoders in general are always more accurate than these. Yeah, but it depends on how big your model is and what data it was trained on. So yeah, how do we pick embeddings? Shout out to Voyage. So typically we are interested in embeddings that perform well across a wide variety of domains and benchmarks. And the sort of most important leaderboard in this is MTAP, Massive Text Embedding benchmark. And basically, you want to look at retrieval here, which is based on the peer data set, which is about 14 different search tasks. And just in the last few months, we have gone up from about 50 to over 60 here. This is actually a few weeks old, so already out of date, right? And you see here a couple of things. You see that there's these kind of smaller models around 500,000, 500 million or 1 billion parameters, and they're kind of being pushed out of the leaderboard at the moment. And you see these large models, which are about 7 billion parameters, and usually based on Mistral or Llama or one of these other sort of more recent pre-trained generative models, and then turned into embedding models. So basically, we want to pick one of these embeddings that is as accurate as possible on our domain. If you're talking about large multinationals, you typically want to look at that it supports many languages.
I have a question about your deployment.
Yeah.
Do you guys host your own models?
Yes.
So you don't use any proprietary models in that case? Because you can't hit a third party.
Pretty much you can do that. So
yeah, that's what, because you have on-prem, right?
You're on-prem.
I see.
That's a little bit out of the question, although companies are usually fine with using Azure or Amazon. Like, so whatever runs in Azure, that's considered kind of okay-ish.
I see.
Okay. But the problem comes after that. And that is all these models are trained on generally available public data sets. So now if you are looking at a domain like chemistry or electronical circuits or legal documents, they're not going to be very good on that. They're kind of good in average on general language. So we want to look at fine-tuning them by looking at the company proprietary data, the data specific to the problem and the terminology. So fine-tuning is easy. You just take the pre-trained model and you do a simple thing with a loss function that has positive examples and negative examples. And basically what you're going to do is move the query and the relevant documents closer together and move the query and irrelevant documents, the red ones, if you remember, further away from each other. And that's going to modify the representational space of the neural network to be better at this task, to kind of learn the domain-specific terminology and the search logic of the domain. For example, from company internal confidential reports. But the problem is, and now we get to your hunch, in most companies, we don't have a lot of supervised training data, right? They're not going to label, 100,000 document query pairs for positives and negatives. So here comes synthetic training data. Basically, every company has documents. They might not have queries. Maybe they have also queries from some query log, but they certainly didn't label the pairs. So we developed together with Rodrigo Nogueira and his team in Brazil, this methodology, which is by now fairly widely adopted in the industry, which we call InPars. And basically in InPars, it started with some parrots. InPars stands for inquisitive parrots. So parrots it's a kind of nickname for large language models and used in search. It's being widely adopted. For example, Google DeepMind's latest embeddings also uses the same approach. And the idea is kind of simple, actually. You always have documents, and you can create passages from those documents, and then you can use a fairly fast and cheap large language model like GPT-3.5, or you can try it with open source ones with good quality. And we're going to generate questions that are answered by that passage. That's a very easy task for a large language model. You don't get hallucinations. It's just you can generate thousands and thousands of documents for passage question pairs.
So InPars helps you do that? InPars helps you do that?
InPars is the methodology and the toolkit.
Okay.
We've actually open sourced the toolkit. And that's a bit more just the prompting. So we do few shots prompting. So we give a few examples of questions that are considered good questions by domain experts, but only a few. And then we generate more questions like that.
One question.
There's a little bit more. You can maybe filter out like the ones which are not really good training material. And then you end up with 100,000 or 10,000 good domain-specific training data.
Yeah, one question.
Yeah.
What if the same question has answers in like different places in a document? So like I've looked at a lot of financial documents. And I feel like if I'm looking at a 10K, for example, like depreciation is something that exists and like there are 10 or 20 pages that talk about it. And there's usually like one or two numbers that I'm really looking at. But does the LLM, do you have to help it understand like what is the right number to be looking at? Because you can get different answers to the same question. And it depends on like what passage or how you really chunked.
Yeah.
How do you solve for that?
Yeah, so you can solve a lot for the cases like that using the examples, right? You can instruct it to not, for example, not take facts which are somewhat ambiguous and then focus on particular terminology, for example, that is important. Because you're not training it here to answer the questions, you're training it more to kind of understand the language of the domain. Right? The answering of the question will still be done at query time using multiple documents and reasoning over them.
Got it. So you're not doing that process to understand what is the right answer. I thought like when you were doing that for different passages, you were saying, okay, this is some answer set or some passage, and you generated like 20 questions out of that. When during query time, someone's asking the same question, that Q&A pair would inform what should be the right passage and what should be the right solution to look at.
Of course, it will kind of bias the representation towards those kind of things, yeah.
But I think to answer your question, I may be wrong, but thing is that I think you have to involve the subject matter expert to kind of pinpoint that these are the key numbers in that paragraph, and then train it more to kind of guide towards those paragraphs to answer. So here, set the initial questions, right? Those extra set of questions and answers, somebody has to validate.
Yeah.
So for example, if numbers are like really important for you, you gotta create sample questions that focus on numbers.
Maybe the point of like
Or if
relevant
molecules are really important for you, you gotta make sure that you generate a lot of molecule and compound name kind of pairs.
Yeah, makes sense.
So there's it's not just like a push of the button. There is some like domain knowledge and a bit of craftsmanship involved in that.
Yeah, just a question on that. How do you measure the accuracy of this particular method versus just not doing it?
We're coming to that right now.
Yeah, I do have a question. So on the previous,
It will be answered in 1 minute. The next slide.
Yeah, no problem.
so so in the previous slide, basically it's kind of a form of transfer learning, because the embedding model is going to absorb the representation space that the LLM knows about.
To some extent, yes.
Right, because I can never, unless I have human annotated data, the embedding model will never have a better representation of the LLM, because the LLM is effectively constructing samples for the representation space that the embedding can learn.
Yeah.
Right?
Yeah, but it's also informed by the content of the actual documents, right? So it's not just distillation from the LLM. That would be if I would ask it to generate both documents and questions, which is also research work which has been done, right? Then you're only distilling the LLM. But if you are taking real pieces of knowledge from the confidential documents, you're doing a little bit more than just distilling.
It's not really distilling. So the idea here is you're creating query document pairs so that you can improve the representation space of the embedding model.
Yeah.
Actually, not only do you want to improve it, but you're trying to do it in a way that is scalable, so you don't have to use humans.
Yeah.
And so therefore the LLM is expressing the relationship between the document and the query.
Right.
It's generating a query
But it's still using language which maybe it doesn't even know, right? Maybe just copying certain strings from the document into here. So yeah, I
You
understand your intuition,
Yeah.
but there's a little bit more power coming from the documents.
Okay, cool. I see.
All right, so once we have these pairs, typically it's sufficient to have a few 10,000s of these pairs, right? You don't need to generate millions. Your effectiveness stops at a certain moment. So we generally use like 10,000 of these pairs. These are positive pairs. I still need to find the negative pairs, and that's really important because you're gonna need to not just take random negatives, but kind of negatives which are kind of similar to the positives. So it's called hard negative mining. And when you have these triples of a query, a positive and a hard negative, then you can use standard fine-tuning stuff to take a open source model and then use this trick to fine tune it.
But the hard negative that you get has to be from outside the domain, right? It cannot be from.
No, from inside the domain.
But how do you know that it is hard negative?
Yeah,
That's a trick.
it's hard because you don't have anybody labeling it.
Correct.
But there, like a general heuristics which works fairly well is to say I'm gonna take the queries. I'm gonna retrieve my documents. Then I'm not gonna take like the top 100, but I'm gonna go a little bit under the top 100, and then that's the document which is similar, but it's probably negative. But there's no guarantee that you also have false negatives, and they kind of mess it up a little bit.
Yeah.
So how many question answers do you need to put a strap that would 10K synthetic?
Only a few, like 5 or 10. I mean, depends a little bit on how much you can get, and there's recent work that shows that for few shot learning, few that is quite large works well, like 10 or 20 or even 100, right? But that also makes it more expensive because you're processing more data. But we found that with 3 or 5, it already works pretty well.
3 or 5 per subject, or because like it could be all types of information.
Yeah, but the information again is not given by the examples, the information is given by the documents. Right, I will show you a few examples.
Okay.
The example is just to train the LLM what to do,
Uh,
or tell the LLM what to do.
We're gonna skip forward a little bit. So these are the type of questions that are created. And then just an infinite, if you have an infinite amount of variety in your documents, you're gonna create an infinite amount of variety of questions like that.
Right,
But
but
of course-
how about the coverage? I mean, there could be other content that will come out only through a fundamental different question.
Sure, yeah,
That's what I'm not talking about variation,
Yeah.
about coverage.
yeah, so if you know more about what kind of questions you can expect, you should put it in the prompt,
Okay.
right? So for example, we have customers, we know that they're also gonna get like keyword questions. Well, then you also wanna put a bit of keyword extraction into the
So
prompt.
like 3 to 5, like similar kind of a, or representative.
Different representative, yeah,
Uh, okay.
yeah, but more is better.
Do you ask it questions related to a certain amount or certain type of text or structure, so like a paragraph versus a certain number of sentences? Because in some documents they're structured in a particular way and
Yeah.
people write in a certain way. So is
That goes again to the point of chunking, right? How do you split the
Yeah.
passages, and can you in your application domain expect questions which span kind of a whole page or a whole chapter, right? Then
Yep.
yeah, that's the kind of stuff you have to do.
It's very complex.
Understand.
Yeah, that's what I was thinking.
Question spans multiple documents.
There's not like something that you can just do a very standard thing and just press the button and then it, yeah, there's a bit of understanding of the domain.
Yeah, there's certain types
and
of
the types
documents as well, right? Which is another
Yeah.
the understanding of the domain. So I'm thinking about recruiting.
Yeah.
Like,
Yeah, if you talk about recruiting,
Yeah.
you probably don't want to slice a person's resume in just 10 lines.
Sure.
Segments, right? There's some logical structure there.
Yeah.
It's more of an art, actually. How you chunk it up.
Yeah.
Otherwise,
So this is kind of just to show you how that it works. And it works really well. So I have an example here from the recruiting domain. But I also have an example from one of our customers in chemistry and one in the legal domain that we did with Deloitte. And basically, the chemistry domain is this is the baseline. It's some older embedding model, and you see that it has a precision at 10 of about 30%. And for German, it's even a lot worse. It's a German chemical company. So when we switched to at that time state-of-the-art model, E5 multilingual, we see that we can improve on that a lot. And by fine-tuning, we improve those embeddings, and especially for German in this case, it almost doubles the precision at that. Because the E5 model has not seen a lot of German training data. And then we add a re-ranker on top of it, and then we fine-tune the re-ranker, the cross-encoder as well. You can do that using the same technique. And then we make a hybrid search, because sometimes lexical match is actually really important, molecules, and add the fine-tune the re-ranker on top of that. And this allowed us to basically increase the precision at 10 from 30 to about 80. That's coming back to the Retrieval-Augmented Generation. That's a really big deal if you're using those top 10 results to template your generative answer.
What is the baseline? It's just dropping documents into LLM?
The baseline is
BM25.
a lexical search
Okay.
and a older generation of embeddings model called mini LM.
Okay.
So the question is like, as you get better and better, why doesn't the German and English catch up? Because your representation of the chemistry is probably in a different space, correct?
Why does the German and English catch up? Maybe German is really complicated. But for sure, the model has not seen a lot of German data during pre-training, like the amount of language, English language that the model has been seen even before it was trained to do embedding. It's just much larger for English. So even in the tokenizer, it has just more representational space for English.
But somewhere at the third or fourth group, you should have started to see them start to closely follow each other, is what I'm saying. The re-rank and everything, the language aspect of it should kind of matter less and less. They should start showing. What I'm saying is finally they should kind of come very close to each other.
No, because the base model doesn't, the English, we have just way more English data, so
they jump that hump, right?
And search in German is just inherently harder, right? They have very long word, compound words. It's just harder for any search technology in some sense. And there might be other things like maybe the type of data that this company has for German is just maybe really old data, or right? So there's no like logical reason they should come together. But I think if you would have an infinite amount of training data, they probably would. And the questions were drawn from the same distribution.
is hybrid search just using the filter, or actually are you actually using dual knowledge bases like a vector and another one?
Yeah, it's just using two queries and then merging them. No. So here on the legal domain, you see something similar. We didn't have an older baseline. You see that the fine-tuning also helps a lot of the embeddings, and then adding all these tricks on top of it helps a lot as well. Here is interesting. We benchmarked it not only against a vanilla E5 model. This is matching jobs and CVs actually based purely on textual representation. And this is precision at 10. And here you see that the fine-tuned E5 model beats also the OpenAI embeddings, the ADA2, the sort of one generation older, by very large margin.
How do you define the precision? Yeah, so what's considered a good output?
Something that a recruiter would consider a candidate worth calling for this job. This case. Yeah. Right. So wrapping up my part, because Fernando will tell you more about the evaluation, some of the engineering parts, but typically the sort of production pipeline with all these tricks is a lot more complicated than the 5 lines of code of RAG in your blog post. There's usually some sort of query pre-processing, intent recognition. If it says summarize this document, you just summarize the document. You don't do a search. All these kind of things. You might want to clean up the query a little bit before you actually send it to the search engine. And then a hybrid search means we do BM25, which is a very good baseline and very robust ranking algorithm. And then we do the fine-tuned embeddings-based semantic search next to it. Then we combine them, we merge those two top search results with reciprocal rank fusion, and then we put the cross-encoder on top. And that's pretty much sort of the winning recipe these days for having a good search engine. Then that final top 10 goes into the RAG prompt to produce the answer. So we have a lot of components here, right? And that's what the rest of this evening
So-
is going to be about.
What does RRF stand for? Actually?
Reciprocal rank fusion. It's a way to merge two sorted lists, basically. And
How do you control the latency with each new component that you add?
yeah. How do you control the latency?
Yeah,
Well, if you take too much here, you're gonna have to earn it back somewhere else, basically,
Yeah.
right? So this whole pipeline, we used to care in search so much about latency that we have any search result which is above 1 second or even above 500 milliseconds is a bad piece of engineering.
Yeah.
But because this generative answer summarization adds so much value, and nowadays we're willing to wait for like 5 to 10 seconds. So you can do a lot of stuff here while this thing is kind of slowing us down.
Okay.
And so we have a lot of components, and that means that evaluation has become more important than ever, right? Prototyping is easy, evaluation is super hard, because every time we change a component, we're gonna have to go back to our chemical research engineers, our lawyers, our product specialists, and ask them to score again these damn top 10 lists of our search results and evaluate the summarized answers of the RAG system. So we have different base embedding models, different ways to fine tune. We have different prompts. We have different LLMs that we can use to generate. It's combinatorial explosion. So we thought, well, maybe large language models are not only the problem, but also the solution to the evaluation.